before we come saying goodbye, we have another talk, I think, by Denis Osin, and he will be talking about hyperbolic use.
Okay, so before beginning the discussion of this then filling group theoretic then filling results, let me remind you two examples of hyperbolically embedded subgroups. So that's what we want to use today. So we discussed the definition yesterday, but now all we know, all we want to use today is just two examples. So first example is that if you have a group G which is hyperbolic relative to some subgroup H, then this is equivalent to saying that H is hyperbolically embedded into G with respect to some finite generating subset, relative generating subset X. And second example, if G is well, let's say G acts acylindrically on a hyperbolic space, and G in G is a lexadromic element, then, so let's call this A. There exists a virtually cyclic subgroup E of G, which contains G, which is hyperbolically embedded into the group G, and part B, for every n, there exists virtually Fn hyperbolically embedded subgroups of G. Not only virtually cyclic, we can also find virtually Fn subgroups. Okay. So now, well, that's just two examples which I will use throughout the lecture today. And now we can state the main theorem about, maybe I'll state it here. Well, this is, all this is extracted from propositions which I stated yesterday. It's just, they were stated as propositions, now just want to think of them as examples of hyperbolically embedded subgroups. So here is a theorem. Let me first state the theorem, then I'll explain what's the relation between this theorem and the original dense surgery in three manifolds. So I'll explain that it indeed, in some sense, generalizes the Thurston theorem. And then I'll talk about some applications. The theorem itself is a little bit technical, but let's state it first. So assume that, suppose that H is a subgroup which is hyperbolically embedded in G with respect to some finite relative generating, sorry, not necessarily finite, just some relative generating set X. So then there exists a finite subset F of H. So it's not a subgroup, it's a subset, which you can think as the analog of the subset of bad slopes. So in Thurston's theorem, you have something which is not true for all slopes, but of all but finitely many. So finitely many slopes are prohibited. That's the analog, such that for every normal subgroup in H satisfying which has empty intersection with this finite subset of bad elements, we have, and now there is a list of statements. So the first statement is that so let's But that's the so-called congruence extension property. So let's take n, and let's take the normal closure of n in G. So this is the normal closure. N is normal in H, but it's not normal in G. So let's take the normal closure of n in G and intersect it back with H. So in general, if you don't assume anything about G and H, this intersection may be the whole H. For example, think about the situation when G is just a simple group and H is some cyclic subgroup, which is not hyperbolically embedded, of course, in this case. But if G is simple, you take H to be cyclic. There are plenty of normal subgroups in H, but for every such normal subgroup, when you take the normal closure in the whole group, because G is simple, you get everything. It's the whole G, so the intersection is the whole H. So in this situation, when H is hyperbolically embedded, it turns out that the intersection is the minimal possible. And of course, minimal possible is n. So what it means, this is actually equivalent to the fact that the natural map from H mod n to G modulo the normal closure of n, let's call it G bar for brevity, is injective. Oh. Right. No. You can allow identity, but then the theorem is obvious, right? So you proved it. Right. Yeah, this is what I always forget. Right. F should not contain the identity element. Otherwise, the proof of the theorem consists of the single line. Take F to consist of the trivial element, then there are no such normal subgroups. The end. Right. So, second condition. So, according to the first condition, you can think of H mod n as a subgroup in this quotient group G bar. And this is the normal closure of n in the group G. Minimal normal subgroup of the group G. Yeah. So I think as H mod n as a subgroup in G bar, and then not only it is embedded into G bar, it's hyperbolically embedded. It remains hyperbolically embedded with respect to X bar, where X bar is the natural image of X. Okay? So then there are lots of other good properties which you can say about this situation. For example, I'll list just two of them. One is that the kernel, so you can ask, well, what's the kernel of the homomorphism from G to G bar, which is exactly the normal closure of n. So what is this? It turns out that it has a very nice structure. It's actually a free product. It's a free product of this sort. So wait, well, maybe before writing it down, before writing the theorem, I should have mentioned that the general slogan is that hyperbolically embedded subgroups behave like free factors. They're not free factors by any means, but they behave like free factors. So think of this situation when G is H star some other group A. Then all these statements become trivial, and actually you can take just trivial subset, so there are no prohibited elements at all. All statements here are true just for any normal subgroup. First two statements are obvious, and the second statement, well, what's the kernel in this situation? It will be just free product of copies of n, right? And it's the same situation here. So it's a free product of conjugates of n by some elements. So there is some subset, let's call it T, transversal. It will be some transversal for cosets of some subgroup, doesn't really matter. But there is some subset T in G such that this kernel is just free product of conjugates of n by elements of that set. Number 4, so in this situation, if you take not just one normal subgroup here, what if you take a sequence of normal subgroups which become smaller and smaller? Then the whole free product is approximated by these quotients, right? So here you have the same situation if n1, okay, let's see, H normal subgroup n1, normal subgroup n2 is a normal series, intersection of ni is trivial, all ni intersect f trivially, then the corresponding kernels ni normal closure in G intersect trivially as well. So the group G is approximated by quotients of this sort. Okay. So that's all what I want to state. But there are lots of other properties which you can prove in this situation. But I think I'll stop here. Yes, I didn't say who proved it. So first, it was proved for relatively hyperbolic groups in my paper. And then there was an independent proof by Daniel Groth and Jason Manning in the case when the group is relatively hyperbolic and, in addition, finitely generated and torsion-free. Then there were several improvements, and the latest one, I mean, in the way I stated it here for hyperbolically embedded subgroups, it's in my paper with François Damani, Vincent Girardel, and myself. So let's try to understand why is it called group theoretic dense surgery? What's the relation between this and dense surgery? Okay, so the simplest situation. Let's assume that, like first application, let's assume that G is hyperbolic relative to H. Okay, so what does the theorem say in this situation? The theorems, well, first of all, according to the first example, this means that H is hyperbolically embedded with respect to some finite generating set, so we can apply the theorem, right? So then, well, the first part remains true, all parts remain true, but what does the second part say? Well, the second part says that the quotient H mod n is hyperbolically embedded in G bar, comma, X bar. If X was a finite set, then the image of a finite set is finite. So X bar is still a finite set. And then according to this first statement here again, this is equivalent to the fact that that G bar is hyperbolic relative to H mod n. Okay. So of course, under the assumptions of the theorem, so you have to assume that n satisfies this condition. And then, so if you start with a relatively hyperbolic group, you take the quotient, you remain relatively hyperbolic. So what's the relation with dense surgery? Okay, let's consider the situation when G is pi1 of a hyperbolic knot complement of n, where n is a hyperbolic knot complement. And in this situation, we consider H, which is pi1 of the boundary of n, which in this case a subgroup of G. Okay. And what is this? Well, the boundary is the torus. So pi1 of the torus is z plus z, everybody knows. And in this situation, it's known that G is Well, if you remember the definition of a hyperbolically embedded subgroup, there was some d hat metric there with respect to which H must be finite. And F consists of elements which are short with respect to that d hat metric. Because H is locally finite with respect to d hat metric, the set is finite. There are some constructive bounds on this length, but I mean, those constructive bounds are generally huge. So you cannot use this kind of approach to show that there are few exceptional surgeries, for example, in 3 manifolds. Instead of real number like 6, 12, whatever, it will give you 10 to the 10 or something like that. Well, maybe it's not 10 to the 10, but it will be huge number, like 1,000, for example. No, yeah, everything is constructive, right? So you can track all the constants. Well, but now there are, I mean, very okay. So in this situation, it's well known that G is hyperbolic relative to H, so we can apply this conclusion. So let's take a slope, which, as you remember, is just an element of H, and let's apply our theorem to the case when n is the subgroup generated by this slope. So because H is abelian, every subgroup is normal there. Okay, then.
Is there a geometric type proof for this where you would get no control of that? As like bigger and smaller and smaller and then it looks more and more like H and G.
Well, it's more or less, so what we are talking about is kind of geometric approximation. That's more or less this statement, which is kind of the analog. This is an algebraic analog of geometric approximation. I mean, that's the best. Well, the method of proof is different from Thurston's because we don't have any true hyperbolic spaces. The method of proof goes, I mean, some parts of it are borrowed from the geometric solution of the Burnside problem by Olshansky, but there are some other parts which are new. So it's just working with diagrams over groups and blah, blah, blah. So it's a true geometric group theory in the sense, well, in the classical sense, like combinatorial group theory. Okay, so in this situation, we have this normal subgroup, and what the conclusion tells us, the conclusion tells us that pi1 of the field manifold, n of sigma, so you remember n of sigma is the manifold which you obtain when you glue a solid torus so that the meridian goes to this sigma. Of course, if you want to get a true manifold, sigma should not be a proper power, but assume we can, well, we are fine with orbifolds, so then we don't care. So pi1 of n of sigma is just pi1 of n modulo the normal closure of sigma, right, in this group, which is exactly our group G bar in this situation. So it is hyperbolic relative to H mod n. Now look, H is Z plus Z. N is a cyclic subgroup here. When you take Z plus Z, mod out a cyclic subgroup, what you get is a virtually cyclic group, right? If sigma is not a proper power, then it's just cyclic. If sigma is a proper power, then it's virtually cyclic. But anyway, so this is virtually cyclic. Virtually cyclic groups are hyperbolic. Now, it's well known that if you have a group which is hyperbolic relative to a hyperbolic subgroup, then the group itself is hyperbolic. Hyperbolic relative to hyperbolic is hyperbolic. So this implies that G bar is hyperbolic. And this is the conclusion of the Thurston theorem, right? That the fundamental group, so this manifold is a closed hyperbolic manifold, which means that its fundamental group is hyperbolic. Well, modular geometrization, there is a backwards implication, so it's a little bit strange to derive Thurston's theorem this way, but you can if you want. So that's why I call it generalization of the Thurston theorem. So here we only use parts 1 and 2. Parts 3 and 4 are not used at all so far. Now I'll discuss a couple other applications, including the application to the Farrell-Jones conjecture. So let's consider the second situation. So suppose we have a group G which acts acylindrically on a hyperbolic space. And suppose that G is a loxodromic element. Remember, L of G is the set of all loxodromic elements with respect to the given action. So now we use the second example over there. So by the second example, there exists, so G is contained in some subgroup, which we denote E of G, which is virtually cyclic, which is hyperbolically embedded in the group G. Okay? Good enough. So what we can do in this situation? So in this situation, we can apply our general theorem to the normal subgroup generated by G to the n. So of course, this virtually cyclic subgroup is not necessarily abelian. So in general, this subgroup is not normal here. But because it's virtually cyclic, for some n, it will be normal. So, and you can make this n as big as you want. As n becomes bigger and bigger, this subgroup n becomes smaller and smaller, so you can always avoid finite subset of elements. Okay? So for every finite subset of elements of E of G minus the identity element, there exists n such that the corresponding subgroup capital N intersects F trivially and n is normal in E of G. So if it's true for some n, it's true for all multiples of this n, so you can take arbitrary large n's here. And then if you apply the theorem, you get the following corollary. So in the situation as described above, let's look at the normal closure of n in the whole group. So now what I want to apply number 3, part 3 of the theorem. So part 3 says that this is a free product of conjugates of n for some subset T of the group G. I don't care about the subset. What I care about is that in my situation, n is just an infinite cyclic group, right? So this free product is just nothing else but the free group of rank infinity. Well, it's not obvious from this statement that it will be of rank infinity, but it's actually obvious from the proof of the theorem. I didn't state it, that this transversal T is always infinite in the non-degenerate cases. So what we get from this, we get the following corollary, which is a simple algebraic statement, but it has lots of applications. So the corollary is that G, where G is as here, which is a group acting acylindrically on a hyperbolic space, has a normal free of infinite rank, purely loxodromic subgroup, normal subgroup. Well, so first of all, of course, the subgroup is normal. It's free of infinite rank. Why is it purely loxodromic? It's another statement which I could add to this theorem, number 5. For every element G in the normal closure of N, G acts on the calligraph Gx union H loxodromically or G is conjugate to an element of N. So if G acts on this relative calligraph loxodromically, then you can derive that the action of G on this original hyperbolic space is loxodromic. And if G is conjugate to an element of N, remember N consists of loxodromic elements, then it's loxodromic just obviously. So one corollary of this is that if you take, say, mapping class group of a closed surface, then it always contains a purely pseudo-Anosov normal subgroups, well, infinite, free of infinite rank normal subgroups. So deriving this corollary was one of the original motivations for developing the whole theory of hyperbolically embedded subgroups, because it was an open question whether every mapping class group like this contains a purely pseudo-Anosov non-trivial normal subgroup. Purely pseudo-Anosov means that every, oh yeah, I didn't explain purely loxodromic. Purely loxodromic means that every non-trivial element is loxodromic. Purely pseudo-Anosov means that every non-trivial element is pseudo-Anosov. So it wasn't even known that whether mapping class groups contain purely pseudo-Anosov non-trivial normal subgroups. So being normal somehow, it doesn't contradict being purely pseudo-Anosov, but it's hard to ensure that this normal subgroup is purely pseudo-Anosov. It wasn't known, so our original motivation was actually to answer this question, but it turned out that the theory has many other applications. So being pseudo-Anosov is the same as being loxodromic if you look at the action on the curve complex, so everything follows. So there are lots of other applications. So for example, results about rigidity, which Martin was talking about yesterday, they also use the existence of such normal subgroup, and you don't need purely loxodromic for that, just infinitely generated free. And there are many other applications. For example, well, maybe I'll mention one analytic application. Yes, it was known, well, in this situation, before our paper, it was only known for G equals 2. It was not known, it was open for G greater than 2. For, if you allow punctures, it was known in some, in few, infinitely many kind of not really exceptional, but infinitely many cases, like sphere with, I don't remember, I think 4 punctures, something like that. Sphere with n punctures, yes. Okay, yeah. So if you allow punctures, it was known for some like small, complex, well, not small, but well, if you allow punctures, it's a little bit easier in a sense. Okay, doesn't matter. So one other application which I want to mention is that, for example, okay, for those who are familiar with the notion of invariant random subgroup, so this fact, just this corollary without purely lexicodromic, just the existence of such free normal subgroups, was used by Bowen, Grigorchuk, and Kurchanov, who showed that for every acylindrically hyperbolic group, for example, for mapping class group, there exist uncountably many ergodic continuous invariant random subgroups. But I don't want to talk about the definition of that. So for those who are interested, I can explain why it is true. It's just a very easy consequence of this corollary and one result about free groups. So another thing is that if you have such a subgroup and the centralizer, let's call it F, okay? And you know that the centralizer of F in G is trivial, which is very easy to verify in these settings. Because every element from this centralizer will also centralize this virtually cyclic subgroup, and then because of malnormality, it should belong to this virtually cyclic subgroup, and then you can easily verify that it's trivial. So the centralizer is trivial. If you have such a free subgroup in your group, in any group, and the centralizer is trivial, then it follows that the reduced C-star algebra of G is simple with unique trace. So the result about C-star simplicity can also be derived from this corollary almost immediately. The implication here is quite elementary. There is nothing difficult, could be explained in like 10 minutes, starting from the definition of a simple C-star algebra. Okay, so there are many other applications which I will not mention. So finally, I'll mention, well, not finally, two more. So one is application which I want to mention is to construct in some monster groups. But because I don't have enough time, I will not really construct interesting monsters. I'll just explain the test case. So if you produce some technique for constructing groups with strange properties, the first test case is, can you do, say, infinite torsion groups, infinite finitely generated torsion groups with your technique, which goes back to the famous Bernstein problem asking whether every finitely generated torsion group is finite. Of course, we know that the answer is negative, and there are lots of constructions now, including some relatively elementary constructions. But still, so it was the original idea of Gromov that you can use hyperbolicity to construct such groups. So this is a theorem which was conjectured by Gromov, and he actually explained the ideas, how to prove it, and then he proved it for fundamental groups of hyperbolic manifolds, then in general situations due to Olshansky. That if G is a non-elementary hyperbolic group, G is an element of G, then there exists an element, there exists a natural number such that if you take G and impose one additional relation, G to the n equals 1, what you get is also non-elementary hyperbolic. So an immediate consequence of this, now you can just enumerate all elements of your group and impose these relations one by one. What you get in the limit is a torsion group. So an immediate consequence of this is that every non-elementary hyperbolic group has an infinite torsion quotient. So this theorem by Gromov and Olshansky, it's an easy consequence of the general theorem stated here. Well, how do we get it? Well, G is non-elementary hyperbolic means that the Cayley graph of G is hyperbolic, so G acts on itself acylindrically, on its Cayley graph acylindrically, and then you just do the same thing as here, right? So you start with an element G. If element G is already of finite order, then we don't care. We just take n to be the order of that element. So basically, the theorem is about elements of infinite order. If G is an element of infinite order, then you can play the same game as here. So you embed it into a virtually cyclic subgroup, which is hyperbolically embedded. You do this, then you take the quotient. So the quotient will be exactly this quotient group, and then you use part 2, which says that the quotient group will be hyperbolic relative to what? In this situation, E of G mod n is just finite, right? So E is a virtually cyclic group, n is subgroup of finite index, you kill it, you get finite subgroup. So in this situation, G will be hyperbolic relative to a finite subgroup, because you can keep this relative hyperbolicity, and therefore it will be just hyperbolic itself. So this theorem actually is a corollary of parts, I think just of part 2. Well, you do need part 1 because you want to keep, there is one thing which you want to take care about, that the quotient group is also non-elementary, not virtually cyclic. This can be done by using part 1, but that's so anyway, I don't want to explain all the details. I just want to mention that you can construct some monsters, and in fact, you can recover a large portion of small cancellation theory by using just this one theorem. What? Well, but Gromov published it 10 years before Delzant. Alshansky published it 1 year before. Delzant published his paper in 1996. What you mean is another, well, he proved this, that's right. Well, modulo the fact that I personally don't understand the proof, and I think there is a gap there. So, but he proved more. He didn't prove, the purpose of the paper was not to prove just this thing. This was already known by that time. I mean, there was already the proof by Alshansky. What Delzant proved that if you take the normal closure of G to the n in exactly this situation, then it's free. And this was another motivation for proving part 4, because we wanted to reprove this result. What? What do you mean? Of course it's no. The original proof, okay, let me say this. Probably there is a way to make it correct, but there is one gap which I don't understand there. And actually, when we wrote our paper, we were trying to mimic the original proof. We failed. So our proof is completely different. It uses something which we call rotation families, which is a completely new notion, which is absent in the Delzant's paper. But probably, I don't want to say that it's incorrect. I think the gap can be filled, but I don't know. Well, the true thing is that I don't understand it. So finally, I just want to mention an application to the Farrell-Jones conjecture, as I promised. The application is the following. So let's assume that we want to prove the Farrell-Jones conjecture for relatively hyperbolic groups, which is already done in the general situation. But suppose we want somehow to recover this result, and I won't prove it in the general form, in the general situation, the most general situation. I'll prove it in the case when peripheral subgroups not only satisfy the Farrell-Jones conjecture, but are also residually finite. So let me now consider, it's, I think, application number, whatever, 3. So let me consider the situation when G is hyperbolic relative to H, and suppose that H is residually finite. Okay? So what it means to be residually finite, it means that we can find subgroups Ni, normal subgroups of finite index in H such that Ni converge to the identity subgroup, which means that intersection of all, so it's a descending normal series, intersection of all Ni's is trivial. So then all quotients G mod the normal closure of Ni. So they are hyperbolic, according to the second statement, they are hyperbolic relative to H mod n, but because Ni is of finite index in H, being hyperbolic relative to a finite subgroup is the same as being hyperbolic. So the second statement implies that in this situation the quotients are hyperbolic. And G is residually so this is an implication of property number 4 that G is residually hyperbolic. Which means that in this situation, when you are hyperbolic relative to a residually finite subgroup, which covers most interesting cases, for example, fundamental groups of hyperbolic knot complements, the peripheral subgroup is just abelian. For general manifolds of complete finite volume manifolds of pinched negative curvature, fundamental groups are virtually nilpotent, still residually finite. So in many, like for limit groups, peripheral subgroups are always free abelian. So in many particular examples of natural particular examples of relatively hyperbolic groups, you have this condition that H is residually finite, and all these groups are residually hyperbolic, which means that if you want to prove some local property, which you can recognize by looking at some finite ball, for a relatively hyperbolic group like this, it's enough to prove this property for for hyperbolic groups, because then you can somehow lift it. For example, if you want to show, if you want to prove something like the idempotent conjecture, right? Existence of idempotence is something, well, in the group algebra, is something which you recognize looking at just by by looking at the finite ball. So if there are no idempotents in hyperbolic groups, then just lift it up. For Farrell-Jones, it's not enough. For Farrell-Jones, if you want to prove the Farrell-Jones conjecture in this situation, then you have to look at just one subgroup, N. So take N as in the theorem, in that main theorem, so it satisfies this condition, avoids finitely many elements. And then you have a short exact sequence it's called G bar 1. So what is G bar? G bar is a hyperbolic group and what is the kernel? The kernel is the free product of conjugates of N. So now the point is that in this situation we do know, okay, so assume in addition that H satisfies the Farrell-Jones conjecture, okay? So since N is a subgroup of H, it also satisfies the Farrell-Jones conjecture, right? And Farrell-Jones conjecture is stable under taking free products. So the kernel satisfies the Farrell-Jones conjecture. And the quotient satisfies the Farrell-Jones conjecture. But that's not enough. As you remember, there is no theorem which says that the Farrell-Jones conjecture is inherited by extensions. What you have to look at pre-images of cyclic subgroups here. And now you need an additional statement which was proved. Well, it was originally proved by I think Giovanni Ganzini and Jaga Antolin, but then there was a mistake in the original proof. So in the paper which is currently in the archive, there is a gap. So this statement is not proved there. But as far as I understand, Rémy Coulon suggested a way to fix it. And right now, so there is a full proof, which I hope will be in the archive soon. So it's not very difficult to fix this problem, but so this is a theorem by Jaga Antolin, Giovanni Ganzini, and I think I should have squeezed Rémy Coulon here. What you need is the following. So in the situation described above, if G bar in G bar is of infinite order, then let's call this surjection epsilon. Then you can describe the preimage of G bar. And the preimage is what you think it should be. So you know that the preimage, of course, it will be generated by G, which is just one element. Right, of the subgroup. Yes. Yeah. So it will be generated by just one preimage of this element. Let's fix some one element in the preimage of the element now. And n, the normal closure of n. The structure of this thing is described here. It's the free product. Now it turns out that you can choose this transversal in such a way that this element G, or more precisely the subgroup generated by this element G, the cyclic subgroup, acts on this free product by permuting the factors. And the action is free. And then you immediately conclude that the subgroup generated by these two things will be isomorphic to the free, infinite cyclic subgroup generated by G, and the free product of conjugate copies of T, but maybe you have to change the transversal. Well, you actually have to take, so if you have G which acts freely by permuting the factors, you just take, instead of transversal, you take quotient modulo the action, and then you take system of representatives, and this is what you get. So this is the theorem, which is an extension of this part 3 of our theorem. Part 3 of our theorem tells you what is the preimage of the trivial element, and this theorem tells you what is the preimage of an element of infinite order. Well, by the way, for elements of finite order in G bar, the same theorem holds true. Well, an appropriate version of it, but it's much easier. It's almost trivial. So it's only for elements of infinite order where you have to work a little bit. And then the Farrell-Jones conjecture follows, because remember, if you know that the Farrell-Jones conjecture holds true for preimages of cyclic subgroups in G bar, then you derive it for the whole group. So here, of course, it holds because, well, this is just cyclic group, and this is free product of groups for which Farrell-Jones holds true. So as a conclusion, you get this corollary that if G is hyperbolic relative to a residually finite subgroup H, and H satisfies the Farrell-Jones conjecture, then G satisfies the Farrell-Jones conjecture. So, of course, this is just a particular result of what Arthur proved, because Arthur proved the same statement without any assumption that H is residually finite, right? It's a more general statement. But I think it's still interesting that you can, in this particular situation, you can derive the Farrell-Jones conjecture just from the fact about hyperbolic groups and some algebraic statements. Okay, I think I'm done.
Thank you very much. Last questions.
T prime? Well, you just take the action of G of this cyclic subgroup on T, and you take representatives of orbits. Yeah, and that's it.
Other questions? It was okay. So I wish you all a safe trip home.